Good day everyone and welcome to today's lecture. It's a rather cold August day, but of course that's the ideal day to have a look at evolutionary algorithms. And today we're going to have a look at evolutionary programming and how that fits into the EA toolbox, how it's put together and how it functions, and of course when to use it. So let's have a look. Now, evolutionary programming is based on the original ideas of Lawrence Fogel, which in the early 1960s was working to develop artificial intelligence from simulated evolution. Now, EPs focuses heavily on phenotypic evolution, which is the evolution of behavioral models. So if you look, for example, at something like a genetic algorithm has a chromosome, which is an abstraction of the solution for the problem that you're trying to solve. And all your operations work on that chromosome. So your crossover, your mutation, etc., all based on that chromosome. And then there's a fitness function that maps that to a solution, or there's a simulation taking place, and then that's how you get to your solution. Now with EPs, which was originally developed to evolve finite state machines, of course it's not the only thing it can do, but it directly manipulated that FSM. So it might change the input symbol or the output symbol or the next state that it might transition to. And because it was changing that behavioral model directly, that's known as phenotypic evolution. And because of this, the only two operators that's used is a selection operator and mutation, which is used as a form of an asexual reproduction to actually manipulate these FSMs or these solutions and to make them better and to improve upon them over time. Now, evolutionary programming uses four main components of evolutionary algorithms. These are, of course, initialization. So just with any other EA, we have to start somewhere. So the initialization generates random individuals or random solutions that needs to cover the search space as uniformly as possible. Then we have mutation, which is the only reproduction operator used by EPs. And of course, that's in other words, an asexual operator. So that's our reproduction. Then, of course, we have an evaluation or a fitness function. And this fitness function attempts to find what's known as the behavioral error of an individual. Remember, it was typically used and initially used for FSMs. And the idea is then, of course, to look at the output of these FSMs and how that differs from the set of test cases that you have. But so that's the fitness function. How good is the solution? And then, of course, the selection operator. And the main purpose of this is to select which individuals survive to the next generation. Now, for EPs, both the parents and the offspring participate in the selection phase. So there's no selection operator to select the parent that's going to be used in this mutation operator. There is a copy that's made of each parent, as you'll see in the next few slides. But of course, then you end up with both parents and individuals or offspring. And from this, you select the next generation. So the basic evolutionary programming algorithm is pretty straightforward. So the first thing that you'll see is that we have the strategy parameter. So the strategy parameter, which we'll see is very, very important for EPs, that gets initialized, and of course also generation counter t equals 0. And then of course the first and very important step is to create and initialize the population C0. So this is the first population generated randomly, and it consists of NS individuals, which of course you have to determine beforehand. Then for each individual, so each individual XIT, which is a member of this population, of course T is 0. So in other words, this is the first iterator that iterates through the population. We calculate the fitness of that individual. So F is the fitness function, calculate the fitness of that individual. So now we know how fit each of them are. Then, of course, the next part is where we actually iterate. So while some stopping condition is not met, so this could be until a solution is found, or the fitness doesn't increase any longer, whatever that might be. So you keep on going. So for each individual, again, so this is again iterator that iterates through the entire population. We create an offspring, xi prime, by applying mutation. So we take this individual, xit, and then of course we create an offspring, xi prime. Then of course we evaluate the fitness of that individual. So now we know how fit that new child is. And we add this individual to the set of offspring, C prime T. So this, of course, starts empty in the beginning, and then we add all the children to this set. And then once you've done all this, so in other words, you've iterated through all the individuals, you select the new population, CT plus 1, in other words, it's going to be C1 now, from the union between the parents and the offspring. So you put them all together, and then you're going to use some kind of selection operator to select those that survive. And that could be rank-based, it could be proportional-based, however you, or even tournament selection, in order to select from that superset the set of individuals that's going to survive. Then, of course, we advance to the next iteration, or the next generation, t equals t plus 1, and then, of course, wash, rinse, repeat. Then we go back to the top of the loop, and we keep on going until we have our until the stopping condition is met, and then, of course, we return the best individual as our solution. Okay, so given what we've seen now from EPs, how does this differ from other EAs? Now, first of all, the most important or the most critical difference is that EPs emphasizes phenotypic evolution instead of genotypic evolution. So genotypic, you modify the chromosome maps to some kind of solution, and there you go. With EPs, you modify that model directly. So the finite state machine is directly modified through a process of mutation. There's no recombination operators. In other words, there's just mutation taking place. Often relative fitness is used, and it makes sense in the case of finite state machines, where you can't really just look at the finite state machine to see how accurate it is. You often compare it with another one to see who is more accurate. But of course, absolute fitness is also perfectly fine. Of course, you can use that as well. Parents and offspring compete for survival together, so there's potentially a large generational gap. There could be a parent that's 3 or 4 or even 5 generations old, because it's just been so fit, so that even the offspring can't compete with it. And then, very importantly, behavior of your evolutionary programming, the way it evolves, is heavily influenced by the strategy parameters. The strategy parameters is a very important concept and a component of evolutionary programming, and that is what we're going to have a look at next. Now, when it comes to the mutation operator in evolutionary programming, it's very important to consider the exploration-exploitation trade-off. And the reason for this is something like genetic algorithms. You have a crossover operator and you've got a mutation operator. And the mutation operator tends to focus more on exploitation, because you've got a very small percentage of mutation that could possibly take place. But with evolutionary programming, mutation is the only reproduction operator. So mutation has to both cater for exploration and exploitation. So exploration is where you search the search space to find good areas or regions where good solutions might be. And then exploitation is where you hone in on that good solution. Now, let's say we've got the following task. Let's say we've got a function. Let's say it's a continuous unconstrained function. So here's f, and it takes a number of input parameters, and that then maps to some real value. So it's a simple equation like f, x, y, z equals, and then one big equation that uses all of that. We want to make that, or get the value for that, to be as small as possible. So it's a very simple, straightforward problem. And of course, you can easily solve that with differential calculus. But of course, now we're going to use an EA to try and to do it in a slightly different way. So then, for each individual xit, I is of course the individual and j is the component. Each of those components are going to be real values, because the input values are real values. So it's that typical idea of phenotypic mapping. So every one of these 3 input values goes through the function, and then you get some real value out. So if it's a 3-dimensional problem, so nx equals 3, then of course j will be 1, 2, and 3, of course, because it's a 3-dimensional problem. So now our mutation can be defined as follows. So given your parent, okay, so your parent is xit. Okay, so xi is the parent and j is every component. You take the parent and you simply add some delta value to each component, and that then becomes your offspring for that parent. Okay, and this delta value that you see over here, this over here, this delta value is known as your step size, and that determines the extent of the mutation. Okay, and of course that step size is a combination of some probability function and some noise that gets added, as well as a strategy parameter. So the strategy parameter, sigma ij, heavily determines how that step size is determined. And of course, that's the focus of the next few slides. So the step size is typically calculated as follows. So it's pretty straightforward. And this is all the components that you really need in your step function. The first is that you've got this phi function, and all that phi is it's just a scaling function. So this just ensures that your step function is not too large or not too small. So it may be some cap function, or it might scale it by multiplying it by some constant value, but it's a simple mapping. So the phi function takes a real value and it outputs a real value. It could also just be a one-to-one mapping, so do absolutely nothing. But it takes the strategy parameter, which of course is the next part, it scales that to some value, and then it multiplies this with this eta ijt value. And this is just noise. This is your noise contribution, or some random value that gets calculated in some way, which gets multiplied by this result from this phi function. And that is your step size. Now, of course, we have to have a look at how this gets calculated. Where does this come from? The strategy parameter, and of course, this noise. How many ways can we calculate that noise? And of course, the product of these, of course, with the phi function that modifies the strategy parameter, that is then our step size that manipulates or is used in the mutation function to generate new offspring for every parent. Okay, so back to the strategy parameters. Now we've seen they could be static, dynamic, or self-adaptive. Now for the static parameters, I mean, there's nothing much really to it. You would simply select a sigma ij that's static at some small value that you're going to use. You'll see in this case, it's actually per component per individual. So that's also possible. You could use a different static value per component per individual, or even the same static value for the entire individual, or even per component, or a combination of that. So, but the point is that you've got a static value. Of course, the main disadvantage here is that it's very difficult to balance your exploration and your exploitation. If your sigma ij is too small, you're not going to have much exploration, and you're probably going to get stuck in a local optima, which is not what you want. But of course, if sigma ij is too large, the algorithm will struggle to converge. So it's going to exploit not exploit good regions, because it's going to jump around and never get to the most optimal solution. It might get a good area, but it's not going to hone in on that local optima in that area. And that, of course, is also a requirement. So that's the problem with your static strategy parameters. So one of the first dynamic approaches was to link the strategy parameter with the individual's fitness. Okay, so your sigma value is equal to the fitness value of the individual scaled by some value. This, of course, assumes that a lower fitness is fitter. So, of course, if you've got a maximization function for your fitness function, then you, of course, need to invert this in order for this to work. But the point is, the fitter the individual becomes over time, the smaller the changes should be that it should make. If it's very unfit, it needs to explore. It needs to jump all over the place in order to find good regions. And the moment it starts to get fit, then of course you start to hone in on that area. And what makes this incredibly powerful is, of course, remember that every individual has its own strategy parameter. So some individuals will use huge jumps, while others would start to hone in on certain areas. So this is excellent for finding those niche areas in a solution space. If you know something about the global optimum, that sometimes is possible. Sometimes you don't know what the solution is, but you know what the fitness would be. Then, of course, you can use that fitness to drive this algorithm a little bit, because you know what the absolute best is going to be. If you don't, you can actually use the best individual. In other words, any individual that's very far from the best individual's fitness must make bigger jumps. That's also possible. And it's also possible to use Euclidean space. So the idea with this is that you would measure the distance in the search space. Let's make it easy. Imagine a three-dimensional search space. And you've got, in somewhere in there, you've got the best individual, and somewhere you've got the least fit individual. You're going to measure the distance between them in space. And that you use as the strategy parameter. So the idea is that if individuals are clumped together in the same area with a similar fitness, then they will make smaller jumps. But if another individual is far away and it has a low fitness, of course, then you use that long distance between that poor individual and the fittest individual to determine how much perturbations you would allow in its offspring, because its strategy parameter would be larger. just be very careful with dynamic approaches is that your step sizes must be controlled to avoid overshoot, because it's quite easy if your fitness is very high, or you don't have something in place to measure that properly to see how it overshoots, then of course it might have a runaway situation. Of course, that you also want to avoid. But that's dynamic strategy parameters. Okay, so as we've seen, mutation has a large effect on the behavior of the model, because that's the only thing that modifies the individual. Now, self-adaptive evolutionary programming allows the strategy parameters to evolve with the solution. And this exhibits true self-organizing behavior. It's actually amazing to see how well this works. Now, within the self-adaptive strategy parameters, you get three kinds. You get additive methods, you get multiplicative methods, and Lognormal methods. So the idea is that this will be applied to the actual strategy parameters to make small changes over time, and then the best values of your sigma ij will then evolve over time. So let's quickly have a look at all three of those values. You'll see the main idea behind it, and you'll see that they are very similar in nature. It's just the way in which those values gets changed over time that is a bit different between the three. So the first self-adaptive technique is that of additive. Now, a common theme that you'll see with all three of these techniques is this part, where the strategy parameters for the child or the offspring, sigma ij t plus 1, is whatever the parent is with some modification. Now, because this is additive, it means we're going to add something to it. Now, what do we add to it? Some value that you see over here. And this value consists of a learning rate. This is this eta value, which is set to a sixth initially, multiplied by the current strategy parameter for that parent, multiplied by a normal distribution. So this is some random value with a mean of 0 and your standard deviation of 1. And that's going to give you both negative values and positive values. And that's how you're going to keep on adapting that strategy parameter. But just be careful, because of the way in which the strategy parameters work, the strategy parameter itself must never be 0 or below. So the moment it's non-positive, okay, so you check it, it's non-positive, just set it to some very small positive value, just so that you don't have these deviations that's 0 or below. Okay, and that's the additive technique. Next, of course, we've got the multiplicative technique. Again, there's that secret recipe where the strategy parameter for the child, sigma ij t plus 1, is whatever the parent is, and this time multiplied by some value. And this is the value in this case. So you've got these lambda values, lambda 1, lambda 2, and lambda 3. In this case, it also considers the number of iterations that you want to use. So over time, it's going to decrease. But the point is, you multiply the parent strategy parameter by some value that you determine with, and then that basically adapts that strategy parameter for the child. And over time, again, you will find that the best ones will evolve. Last but not least, we've got Lognormal. Now, in this case, you multiply the parent strategy parameter with e to the power raised to a power of some value. And this value is determined by these two tau values, tau and tau prime, together with a normal distribution. There's a normal distribution over here as well as over here. And these two tau values are calculated based on this. And it takes into both consideration the number of dimensions of the problem, and that is then used to scale that value. Very importantly is to have your normal distributions. You have that little bit of randomness as well. But that's Lognormal for self-adaptive. Now, self-adaptive EP has showed the undesirable behavior of stagnation. In other words, it doesn't really make any progress, and the reason for that is the strategy parameters tends to converge faster than the actual solution that you want to evolve. And the way to circumvent that, of course, is to put a lower bound on sigma ij. So when it drops below a certain value, you just cap it to make sure that there is at least some kind of mutation that keeps on occurring, so that there's progress that can be made. So in terms of your selection operators, EP, because of the kinds of problems it often is used to solve, we have to make use of relative fitness. Now remember, relative fitness is, you don't always have an absolute value or an absolute value that can be associated with a value. You compare the individuals with one another, and that way you find which one is which. Now, quite often you'll see in EP literature, they use this me and lambda to indicate the number of parents versus the population size versus the number of offspring. We'll just keep on using that notation here as well. So the first step is to calculate the relative fitness for each parent and, of course, each offspring. So that's that xit and xit prime. Okay. So first of all, we define this competition pool. So this is this PT. And that is essentially all the parents and all the children, all the offspring. So it's just basically all of them together. And then we select an individual, UIT, from this competition pool. And you're going to iterate through the entire competition pool to basically determine the fitness for each of them. So this is what you see over here. This I goes from 1, the first individual, to the last one, which is me plus lambda. Of course, you've got the offspring, which is the lambda, and the parents, which is me. Okay, so then for each of these elements, each of these individuals, which is a member of that, you select a competitor pool. Okay, and the competitor pool, NP, is essentially a random number of individuals that you choose. And then what you do is you compare FUIT with FULT. In other words, the individual that you are trying to find the fitness for versus the competitor. And then if the fitness of this individual is better, you give it a score of 1, otherwise 0, and then you add them all up. So you could perhaps have a scenario where you select 10 competitors, and then if the individual that you want to measure the fitness for is better than all 10, so maybe there's competition that it competes with one another. It could be let's say, for example, it's a tic-tac-toe or something like that. If it's able to beat all of those competitors, it will get a score of 10. If it gets 0, it means it couldn't beat any one of those. It is 0, and if it's 5, perhaps, then it was able to beat half of them. So that's relative fitness. So in the end of this, you won't be able to say, or to take this individual and give it a specific score just based on itself. You have to compare it relatively to the other individuals in the population pool. And that's how we do our selection. So in this way, we know which ones are better than which. And of course, now we can then apply some kind of selection operator like proportional or selection or rank-based, whatever the case may be, to actually then go and select the individuals that's going to survive to the next generation. And then, of course, once you've got the fitness, as I've said, you could use elitism, you could use tournament, proportional, rank-based, any of the standard selection schemes to select the individuals that will survive to the next generation. Guys, and that's evolutionary programming. I hope you enjoyed that and you found that useful. Please have a look out at the demonstration program I'm going to upload. It's a case study on the iterated prisoner's dilemma and how we can use EP to evolve finite state automata to actually solve that. It evolves agents that can come up with good strategies to play the iterated prisoner's dilemma. That's it. Keep well and happy coding.